go. All right. So we're going to be talking a lot about these terms: scalar, vector, distance, displacement, speed, velocity, and acceleration. And we're going to basically learn what are scalars and vectors, what are the differences between distance and displacement, speed and velocity. We're going to become able to calculate them, and we're going to become proficient in using the 1D equations of motion in order to solve problems. And here they are. I handwrote them and uploaded them. So this is what we're going to be using for the 1D part of our kinematics unit. So scalars are basically quantities that are fully described by a magnitude alone or a numerical value. So if I say 100 meters or 52 kilograms, something like that, or 10 degrees Celsius, those are all scalars. They are fully described by giving a number. Now vectors need both a magnitude or number and a direction in order to be fully described. So for instance, in this picture here, if I tell you to go ahead and walk 100 meters to the store, the first question you're probably going to ask me is 100 meters in which direction? But if I tell you go ahead and walk 100 meters to the north and you will find the store, that's a different situation. You're going to know exactly where to go and you're going to find the store right away. Whereas here, 100 meters, not knowing which direction, that's incomplete information. All right, so why don't you, when you go through these slides on your own at home, give these a try. See if you can distinguish what's a scalar and what's a vector. All right, so now we're going to talk about displacement and distance. So I think many people confuse these. They're similar, but they're not the same. So distance is a scalar quantity. It is described by a number alone, and it basically describes the total distance traveled by an object along the path that the object actually took. Whereas displacement is a vector quantity. It really tells us how far did the object get from wherever it started to the point where it ended. Displacement doesn't really care how the object got from point A to point B. It really cares about the final position. What is the final position relative to the initial position? And so, you need to tell us a distance and a direction. Here's the equation for displacement. Let's do an example to kind of clarify everything. Let's say we have a car that starts at 0 over here and it travels 70 meters to the east and then turns around and travels 30 meters back to the west. So the total distance that this car actually traveled is 70 meters plus 30 meters. Okay, that's 100 meters. That's the total distance that the car actually traveled. The displacement, on the other hand, if we look at where the car started at 0 and where the car actually ended up, the car ended up at 40 meters over here. I don't care how the car got there. I don't care if it took a super long path, or what matters for displacement is the end point and the start point. All right, so in this example, the displacement would be the end point, which is 40 minus 0, the beginning point, that's 40 meters, in the positive x direction, or we can say in the east direction. That's very important. We need to specify the direction. All right, so similar to distance and displacement, we have speed and velocity that are very often confused by people. Again, speed is a scalar, so when we talk about speed, we talk about a value, a number value. It's like being inside your car and you're going 60 miles per hour, but you may not know exactly if you're going east or west or whatever. You just know that you're going 60 miles an hour. So that's speed. And the formula for speed is distance traveled by time, divided by time. Velocity, on the other hand, is much more used in physics. We're going to use it way more than the speed. It's a vector quantity, so we can't just say a number. If I ask you what the velocity of your car is, or a plane actually makes more, it's more intuitive for people. If I ask what the velocity of a plane is, you can't just say it's 300 kilometers an hour. You have to say 300 kilometers an hour to the north. And think about planes flying in the sky. It's very important that they know the direction they're going. They can't just go in random directions, or else there will be an accident. So velocity has that direction component to it. And to calculate velocity, again, we divide displacement by the time elapsed. So examples of velocity would be 60 miles per hour to the north, or we can say plus 60 miles per hour or minus 60 miles per hour. And what that means, plus is telling me that I'm going 60 miles per hour in the positive direction, which is along a certain axis that I have set up to be the positive direction. And we'll talk more about that. Whereas minus 60 miles per hour, that tells me I'm also traveling 60 miles per hour, but now I'm going in the negative direction. All right, so let us skip to this, which is velocity and acceleration. Again, two quantities that sometimes people confuse. So velocity is the rate of change of distance, whereas acceleration is the rate of change of velocity. So let's say I'm starting up in my car and I'm going from 0 miles per hour, and now I'm going to 10 and 20, right? I'm going higher and higher. I'm accelerating. That's what it means. I'm accelerating. That means my velocity is changing. I'm not just going at 10 miles per hour the entire time. I'm going 10, and then I'm going 20, then I'm going 30, and all of this is happening over a given amount of time. So that's how we define acceleration. So here's the formula for it. So acceleration could be both speeding up and slowing down. What matters is that the velocity is changing. So if I'm just traveling in my car and my velocity is not changing, that means my speed is not changing, my direction is not changing. I'm always going at 60 miles per hour in the exact same direction. Then I have zero acceleration because my velocity is not changing. But if I'm speeding up, so let's say I'm going from 60 to 70, or even if I'm changing direction, that's a change in velocity. Or if I'm slowing down, let's say I'm slowing down from 60 to 40, now we have an acceleration. And these are dot diagrams that we'll be talking a lot more about. But basically what these guys show us is these dots show the position of the object, whatever object we're talking about. These dots are showing me where the object is at every second. So if the object is here, then it's moved here, then a second later is here, another second later is here. So what I'm seeing here with these green arrows, what they're showing me is the velocity, right? Because look, in this 1 second, it covered quite a bit of distance. And then in the next second, it covered a little bit less. So it's got a little bit less velocity. And then the very next second, it's going even less and even less. So it's slowing down this object. So my green arrows are showing me the velocity, whereas this orange arrow on the bottom, I don't know if you can see it, but there's an orange arrow that is the acceleration, and that is actually pointing opposite to the velocity. And why is that? Because in order for the velocity to slow down, in order for this object to slow down, the acceleration has to act in the opposite direction of the velocity. Similarly, we got this other object here going in the negative direction, and we can see that it's here, and then a second later it's here, and then a second later it travels even a bit further, another second later even further. So this object is actually speeding up. That's what the green arrows are showing us, is that it's speeding up in this negative direction towards the left. And if it's speeding up like that, then the acceleration has to act in the same direction as the velocity, because that's the only way for it to speed up. Whoops. All right, so let's go here, for instance, and of course, what it said, let's see if I can get it. Acceleration is a vector because, as we've seen in the example before, it has a magnitude. So it gives us a number, but also we have a direction. We know that it has to act in the same direction as the velocity if the object is speeding up, and it's got to act in the opposite sense of the velocity if the object is actually slowing down. So in this example, it's showing us this car, which at t1 equals 0, the initial time is going at 15 meters per second. And then a little bit later, 5 seconds later, t2, it's going at a velocity of 5 meters per second. So the acceleration, we look at our formula over here, is the change in velocity, which went from 15 to 5. So that change was 5 minus 15 is minus 10, divided by the change in time. So the change in time from 0 to 5 seconds. So we got minus 10 divided by 5 seconds. We got minus 2 meters per second squared. And notice that we're getting this minus here, which is telling us that the acceleration is going in the negative direction, and it's opposite to the direction of the velocity. That's why the car is slowing down. You can see it's slowing down from 15 to 5 meters per second. All right, so we'll go through these another time. I'm going to stop this video here, and we will see you guys next time.